All right, let's move on to the next section, 11.2. Now, this is called a goodness of fit hypothesis test. All right, so what is a goodness of fit hypothesis test? So it's used to determine whether the data fits a particular distribution or not. For example, you may suspect your unknown data fits a binomial distribution, so one uses a goodness of fit test to find out. The goodness of fit hypothesis test is a right-tailed chi-square distribution test. The degrees of freedom are calculated this way. So degrees of freedom is equal to k minus 1, where k is the number of different data cells or categories. So it's a little different than sample size. Okay, this is not sample size. That's why we're using a different variable to denote this value. You'll see an example, so I think that'll clarify what K represents. The null and the alternate hypotheses may be written in sentences or equations or inequalities. Like any hypothesis test, one needs a test statistic related to the sample data. Now, the formula for calculating the test statistic is this formula, this equation right here. So notice that there's two letters, O and E. So this letter O, this variable O, represents observed values. So that's data that you've collected. That's like your sample data. Now, E is a variable that represents the expected values. So again, we're trying to see if the shape or the distribution of our sample data matches the shape of a given distribution. So we want to see if they match. And once again, K just represents the number of categories. Okay. And let's see here. Okay. So the expected values. So the expected values will be determined by whether the anticipated distribution to be fitted is either uniform or non-uniform. So if the expected values are uniform, that means each category has equal probabilities of occurring. If the expected values are non-uniform, then at least one category has an unequal probability of occurring. And depending on which scenario you're looking at, the expected value will be calculated using this equation, or if it's non-uniform, the expected value will be calculated using that equation. So let me use maybe different colors to differentiate here. All right. And again, you're going to see an example of calculating expected values both ways. Okay. Now, just like any other hypothesis test, we calculate a critical value. And the critical value, separates the significance level from the confidence level, and it also separates the reject the null and the fail to reject the null regions. Now, typically a chi-squared table is used. However, I've written a program called inverse chi-squared 83. So this inverse chi-squared 83 is not a native Texas Instruments application. It needs to be installed onto your calculator. But if you're in my class, I've installed it for you. So what this will do is this will allow you to convert your significance level into a chi-squared critical value. Okay, that's what this function is for. And you'll see an example of how that works. So remember, the null hypothesis should be, let's see here, that the sample fits the chosen distribution. Consequently, the observed values should be equal to or approximately equal to the expected values. Okay, here's that chi-squared function again. Okay, I'm trying to scroll down here. All right. Having the observed and the expected values approximately 0 in this expression here makes the numerator close to 0, which makes the entire expression close to 0. And the sum of these close to 0 terms will create a test statistic that is small. So locating chi-squared test to the left of the x critical value or the chi critical value, resulting in a fail to reject result. Okay, so that may be somewhat cryptic, but let's try and look at a visual here. And I think you'll see that this looks familiar to other hypothesis tests that you've already done. As soon as I'm allowed to scroll down, here we go. So here we have an illustration of a chi-squared distribution here. And you can see we've got a chi critical value, and the critical value separates the significance level from the confidence level, and the reject the null region is over the tail, and the fail to reject region is over the confidence level. And so what we need to do is we need to calculate this test statistic, okay, using this formula up above, right? We use this formula to get our test statistic, and we see whether it lands on this side or that side of the critical value. Now, don't worry, the calculator is going to calculate this test statistic for you, okay? But you will need to know what the observed values are and specifically what the expected values are, because you'll have to put those into your calculator. Okay. So I think that's enough of a heads up. The next video is actually going to show you how to do a goodness of fit test. Also as a heads up, if you're using a Texas Instruments 83 calculator, it does not have a native chi-squared goodness of fit test function in it. But I have written a program which functions, that has an equal function, okay, to the more modern models. All right. So I'll demonstrate that as well. Okay, so let's stop there. Let me know if you have any questions.